sign. Once again, MF equals negative n delta phi over delta t. What about the negative sign? The negative sign in the previous relation indicates that the direction of the induced EMF and direction of the induced current is opposing to the change producing the induced current. This is Lenz's rule. So talking about Lenz's rule or Lenz's law, and it is very important. What about it? Okay. The induced current flows in such a direction to oppose the motion or to oppose the change producing the induced current. This was about the statement of Lenz's law. Let me say it again. It is very important. The induced current flows in such a direction to oppose the motion or a change producing the induced current. And now let's demonstrate, Lenz's law. So an experiment to explain it. In front of you, we've got a coil which is connected to a center zero galvanometer. Okay? And a magnet is moved with the north pole towards the coil. Okay? So while moving the N pole towards the coil, an EMF is induced and current flows. And you see that N pole is produced near the pole of the magnet. North pole, when we approach North Pole. And what happens when we remove the North Pole away from the magnet? And now the current opposes the removal of the North Pole. So S pole is produced. Once again, when North Pole is approached, is plunged into the coil, the induced current, opposes the approaching of the North Pole and N pole is produced. Okay? When removing the North Pole, S pole is produced. So, when the North Pole of a magnet is plunged into the coil, the induced current in the coil flows in such a direction, such as to produce a North Pole at the end of the coil facing the North Pole of the magnet, so as to resist, to oppose the approaching of the North Pole. The repulsion force between the two like poles resists the approaching of the North Pole of the magnet. Okay, when the North Pole is pulled away from the coil, the direction of the induced current is reversed to produce a South Pole at the end of the coil facing the North Pole of the magnet to oppose the removal of the South Pole of the magnet. We've got something very important to mention here. Okay. Lenz's law determines the direction of the induced current in a coil. And you should be able to differentiate between Lenz's law or Lenz's rule and Fleming right hand. Both of them are used to determine the direction of the induced current. But Lenz used it to determine direction of the induced current in a coil, and Fleming right in a straight wire. So once again, Lenz is used to determine the direction of the induced current in a coil. And now talking about determination of the induced current in a straight wire. We'll use, as I said, Fleming's right-hand rule. What about the statement of Fleming's right-hand rule? If the first three fingers of the right hand are held mutually perpendicular, are held at right angles to each other, with the forefinger pointing in the direction of field, forefinger pointing in the direction of the field, and thumb in the direction of motion. Okay, second finger will give the direction of the induced current. The second finger points in the direction of the induced current. This was about Fleming's right-hand rule. And now let's make a comparison between, Fleming left and Fleming's right-hand rule. Okay, what about Fleming's left? It is applied when a current causes motion. We first let a current passes, then we've got a force. So it is applied when a current causes motion. And what about the right-hand rule? Fleming's right hand, it is applied when motion induces current. Okay. Fleming's left, is used for the determination. It determines the direction of motion of a current carrying a straight wire placed perpendicular to a magnetic field. And what about Fleming's right hand? It determines the direction of the induced current in a straight wire. And now talking about a phenomenon known as mutual induction. What about mutual induction? It is the generation of an induced EMF in one circuit as a result of the change in the magnetic field of another nearby circuit. So in one circuit current changes, in other circuit a current is induced. Okay. And now talking about various methods for obtaining current by mutual induction. So we've got an experiment. Actually experiments, and they are very important. The figure shows, in front of you we've got two coils. One of them is called the primary coil, in which we've got a coil connected to a supply, DC supply, battery, rheostat, and switch. And we've got a secondary coil. What about the secondary coil? It is the coil which is connected to a center zero galvanometer. Secondary coil does not, contain a supply, a source of electricity, a DC supply. It doesn't contain it. So the primary circuit that contains, cell, switch, rheostat, and a coil. We call it primary coil. And what about the secondary circuit? It contains a coil of wider area, greater number of turns on it, and center zero galvanometer. And now what about the methods to obtain currents by, mutual induction? There is an EMF induced in the secondary circuit in the instant that the current in the primary circuit is turned on and off without moving, either coil. So the first two methods, the primary current is turned on and off. Also, the current in the primary circuit is increased or decreased. The question is how to increase it or decrease it. Yes, of course, it's all easy by using the rheostat. And these are the third and fourth methods. By increasing or decreasing the current flowing in the primary coil. And what about the last two methods? The primary coil is turned on and either coil is moved towards or away from the other. So by moving the primary coil, yes, towards the secondary or away from it. Observations. The needle of the galvanometer swings to one particular side in the instant that, the current in the primary circuit is switched on. Current in the primary circuit is increased. The switched on primary coil is pushed into the secondary. This means we've got the same direction of deflection. The needle of the galvanometer deflects in the same direction. When approaching the primary coil, when the current in the primary is increased, and when switching the current in the primary on. In these three cases, the current induced in the secondary coil flows in an opposite direction, backward current we call it, to that flowing in the primary circuit. So let me say it again. In these three cases, the current induced in the secondary coil flows in an opposite direction to the current flowing in the primary coil. That is to say, the EMF and thus the induced current opposes the increase in the magnetic field linking the secondary coil. When we increase the primary current, when we switch it on, when we approach the primary circuit towards the secondary, there is an increase in the magnetic field linking the secondary coil. So the induced current opposes this increase. Of course, this is the statement of, thank you very much, Lenz's rule. The induced current takes the direction such as to weaken the magnetic field linking the secondary coil when the field through the secondary coil increases. Also, your attention please. We observed that the needle of the galvanometer swings to the opposite side in the instant that we've got another three cases. Yes, when the current of the primary circuit is switched off, current, of the primary is decreased. The primary circuit, which is energized, is moved away from the secondary. The current induced in the secondary coil flows in the same direction as that of the current in the primary circuit. So it is a forward current. The forward current opposes the decrease in the magnetic field linking the secondary coil. The induced current flows in a way such as to strengthen the magnetic field linking the secondary coil when the field collapses. This agrees completely with, Lenz's rule. And now talking about the methods to increase or how to increase the EMF induced in a coil by mutual induction. So talking about increasing the EMF induced by mutual induction. Yes, first of all, the induced EMF and thus the current can be increased by cutting more flux lines in a certain time. And this can be achieved by using a larger secondary coil of many turns, and by winding the coil on a soft iron core. Also by placing the primary coil inside the secondary coil. Also by strengthening the electromagnet by using iron core, by adding more turns, or by increasing the current through the coil. Also, it can be achieved by closing and opening the electromagnet circuit rapidly, thus cutting lines of the magnetic field faster, in a faster way. And now the EMF induced in the secondary coil is given by, so now talking about the expressions, the mathematical relation that gives the EMF induced, okay, in the secondary coil. EMF, yes, 2 is proportional to delta I1 over delta T. Delta I1 over delta T, rate of change of the current in the primary coil. Okay, so EMF is equal to negative sign M delta I over delta T. M indicates mutual inductance, or we can say it is coefficient of mutual induction, where M is the coefficient of mutual induction, or as I said, mutual inductance. EMF, as I said, is equal to N, number of turns on the secondary coil, delta phi over delta T. Yes, this is from Faraday's law. So from equation 1 and equation 2, we can say N secondary delta phi magnetic over delta T is equal to M delta I1 over delta T. And of course, delta T will be crossed out. In this case, we can say M is equal to number of turns on the secondary, delta phi magnetic over delta I1. So what about mutual inductance of two coils? Okay, mutual inductance of two coils is the EMF induced in the secondary coil. It is EMF induced in the secondary coil. When the current in the primary, it changes at a rate of 1 ampere per second. So it is the EMF induced in the secondary coil when the current in the primary changes at a rate of 1 ampere per second. Since EMF on the secondary coil is equal to minus M delta I1 over delta T, delta I1 over delta T in the primary. So talking about the units, EMF is measured in volt, any inductance is measured in Henry, current in ampere, and of course time in seconds. So volt is equal to Henry ampere, yes, second negative 1, or Henry ampere per second. Okay, and of course we can say Henry is equal to second times ohm, because volt over ampere, potential difference over current intensity is resistance, and it is measured in ohm. So this is very important. Talking about units, Henry is equivalent to second times ohm. Henry, as I said, is the SI unit of mutual inductance. SI means the unit according to the international system. What about the definition of Henry? Yes, it is the mutual inductance of two coils. If let me say it again, it is the mutual inductance of two coils. if an EMF of 1 volt is induced in the secondary coil, when the current in the primary, it changes at a rate of 1 ampere per second. This was the definition of Henry based on mutual induction. And now we've got a question, what's meant by the mutual inductance of 2 coils is 0.3 Henry. Let me say it again. The question is, what's meant by the mutual inductance of 2 coils is 0.3 Henry. It means that an EMF of 0.3 volt is induced in the secondary coil when the current in the primary changes at a rate of 1 ampere per second. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.